we're going to go through this and we're going to actually combine arithmetic sequences, which we already know, with geometric sequences. Okay, so as we go through, you're going to do two things at once, just make comparisons between the two different types of sequences. So first thing, this explore section at the top, I want you to work through with your table group just through the two tables and the two questions below it, just so you can kind of get an idea of the difference between an arithmetic and a geometric. So my sequence on the left, was that my arithmetic or my geometric?
Arithmetic.
Arithmetic. That's like the ones that we did earlier this semester, right? So what was my sixth term?
Sixth term was 13.
And then my seventh term?
15.
Okay, what would the next two terms be based on that pattern?
8.
On? Wait, what?
Isn't it 13?
17.
Oh, after
17,
that?
19.
And 19.
Oh, I thought it was 17.
Yeah, I thought
those were the two.
Yeah, because I thought like 6, 7, that's what I did.
Oh, okay, well. And then my second sequence was not like one we've done before, so that is for geometric. And what was different about that sequence?
It's multiplying by
You were multiplying by 2. So my sixth term was what?
96.
96. And my seventh term was
192.
192. What would my next two terms be for that? 384 and
768.
Good. Okay, so how are the two sequences alike?
They both have sequence.
Okay, patterns.
They're both positive.
They're both positive. They're increasing.
They both have a correlation, maybe.
No, you're relating something different.
Yeah, I think I am.
Eric?
Let's have a turn number.
Okay.
They both have a y-intercept.
Okay. What is the first term of each of them?
3.
Good. How are they different?
One's multiplying.
Okay. So the geometric was multiplying. And the arithmetic was doing what?
Adding.
Good. That was really the biggest takeaway from that, right? Okay, so as we go down, we talk about this recursive rule. Y'all probably don't remember exactly the recursive rule, but it rings a bell, right?
Yeah.
So your recursive rule is the one that tells you, here you are, how do you get to the next term? It helps you find the first few terms. It does not help you find like the 100th term. It is the actual process to get from one term to the other. So our arithmetic recursive rule, remember you have to list the first term. They didn't put that in there, but you have to list the first term because how do you know where you're going if you don't know where to start? So the first term, and then your f of n equals f of n minus 1, which is just the previous term plus d, where d is the common difference. So looking back at that first sequence that you guys just finished for me that I didn't paint, what was our common difference?
2.
2. So my recursive rule would be the first term, which is what? What was the first term?
3.
3. And then every term thereafter, f of n, is the previous term, f of n minus 1 plus 2. Now, remember when we did sequences the first time, and this part of your function of a recursive rule never changes. You're just plugging in the common difference at the end. Does that kind of bring back some memories? Alright, so now the only thing different in your recursive rule for a geometric sequence is the process. We weren't adding for geometric sequences. What were we doing? Multiplying. So my first term is still 3, and I still need to use the previous term to get to the next term. But instead of adding 2, I'm going to multiply by 2.
Don't you have to
So that is your recursive rule. Only thing that's different is the operation. Okay, so now let's compare these sequences when they're graphed. We'll start with the arithmetic. What was my first term of my arithmetic sequence? 3. So the first term was 3. We're kind of just eyeballing it a little bit. What was my second term? 5. What was my third term? 7. And my fourth term? 9. And my fifth term? 11.
Everything's kind of blinking.
What kind of pattern does that make on my graph? It's linear. So my arithmetic sequence is linear. Let's look at the geometric. So what was my first term?
3.
3. It was the same. But my second term is 6, already a little bit bigger. My third term?
12.
12. And my fourth term? And then 48.
It's kind of gross from there, yeah.
Okay, is that linear?
No.
No.
Oh.
That is an exponential growth. Okay, what kind of descriptions could you make about my graphs? I have 2 things graphed there, 2 functions, or 2 sequences.
They both function.
Okay, they're both functions. What else? Is one growing faster than the other?
Yeah.
Which one's growing faster than the
The
other?
geometry.
Which one has a constant rate of change? Arithmetic. Good. All right. We good to move forward? All right. Flip it over. We're going to talk about some definitions, and I promise I won't make you write a whole bunch. We're going to take a basic definition. We're going to expand on it. So our basic definition, a sequence, is a pattern of numbers or values, which a lot of times when you first learned sequences, right, it was in pictures, but those were still values, right? You have to count the triangles or count the squares or count whatever. Now, an arithmetic sequence is going to start off with the same definition, and the geometric sequence is going to start off with the same definition. So if you haven't seen this before, you can just say the same, but we're going to expand. Have y'all seen the apostrophes used as the
Yes,
same?
ma'am.
All right.
We learned about it in English class, 6th grade.
Oh, good.
First 6 weeks. Third week of first 6 weeks.
Oh, please. All right. So
Tuesday.
arithmetic sequence. So if I'm taking a sequence definition and I'm expanding it to say arithmetic sequence, what does the word arithmetic change or not? What does it add to my definition? What's more specific about arithmetic sequences? Y'all just graphed it, you talked about it.
Linear.
That is linear. It has a constant rate of change.
Geometric.
And we're going to put there your adding. Because that's our main takeaway. When you look at the different rules, you're looking at, does it add or does it multiply?
Yeah.
Our common difference, a lot of sequences relate nicely into other parts of our content, right? So when we did arithmetic sequences, we led them into linear functions. So that the difference is also called your slope.
No. Oh, I get you.
Okay, and now we're doing geometric sequences, and our geometric sequences are going to lead us really nicely into exponential functions. So that ratio is also called the growth or decay factor.
What is the decay factor?
If it's increasing, it's growth. If it's decreasing, it's decay. Okay, so let's finish the definition, and then we'll be done with the writing section. Okay, our geometric sequence is a pattern of numbers or values that uses a common factor.
I always do not get what a factor is.
Factor is multiplying.
I know. Now I do. I was talking about like.
And we're going to write multiply. Okay, so at your table, look through 1 through 6 and just label. You don't have to write out the whole word, arithmetic, geometric, or neither. You need to decide, is it adding, is it multiplying, or does nothing apply? What kind of sequence it is. Okay, let's bring it back together. Number 1.
A.
Arithmetic, you're adding 5. 2.
Geometric.
Geometric. 3.
Geometric.
4. Arithmetic, you're subtracting 4. Number 5. Neither. 6. Neither. Okay. Now, these are your explicit formulas.
Oh, I forgot about this.
A of n is any term on both. So that's the same. What's A of 1? First term. On both. What's D? Difference. What's R? Ratio. It's your factor or your ratio. Those are the same.
So I got it right?
Yes. Okay, so now we're going to do a couple together. I'm going to skip through. Anything that I skip becomes your homework. Okay? So, looking at number 1, A of n equals 3n plus 2. We're writing the first 6 terms and stating whether the sequence is arithmetic or geometric. 3n plus 2, arithmetic or geometric? That is arithmetic.
A, because there's an addition sign.
Okay,
We have to write out the whole thing.
what is the common difference? No.
3.
The multiplier is your common difference. What's your first term?
2.
No.
1.
0.
Okay, time out. This is not the expanded form. That is slope-intercept form. So if I want to find my first term, what do I need to do? Plug it in as n. So my n is 1. If I put in 1 for 3n plus 2, what is my first term? 5. So my second term would be
7.
8. My third term, 11. My fourth term,
Wait. Miss. Oh, it's plus 3.
yes,
I got you.
17 and 20. Very good. Now, I said that that was the simplified, it's not the expanded form, it's the simplified form. The nice thing about geometric sequences is there's no such thing as an expanded or a simplified. It's just one form. You need to add in, though, on number 2, this should say n minus 1. No, it doesn't need to be in parentheses, it's an exponent. Okay, so what is that arithmetic or geometric?
Geometric.
Geometric.
Oh.
Okay, what's my common ratio? 2. What is my first term? 3. So if my ratio is 2, what is my second term?
6.
6. And my third term? 12. And my fourth term?
44.
Good. And then 48. And then 96.
Oh, yeah,
Very good. Okay. Flip it on over. I'm not going to do 3 and 4 with you, but I need you to change this to say n minus 1 for number 3, so when you go back to do it later, that it makes sense. Okay? And we're going to do 1 towards the very bottom together. Let's look at this bottom section. Identify each sequence as arithmetic or geometric, then write an explicit and recursive formula for the following sequence. Take a second and look at those and pick out one for us that is geometric. Or no?
Number press.
Number 3. Okay, why is that geometric?
There's a lot of big numbers.
That doesn't mean that it's geometric.
And it's multiplying.
It's multiplying. What are we multiplying by?
3.
3. It is geometric. My ratio is 3. So let's start with the shorter of the 2 rules, that explicit rule. So I need my first term. What's my first term?
25.
25. So this is f of n equals 25 times my common ratio, which is 3 to the power of n minus 1.
Oh, that's it?
And you're done. That's it. You can't simplify it. There's nothing you can do to it. And please, 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 you cannot do 25 times 3 to the power of n minus 1. You can't make that 75 to the power of n minus 1. Because order of operation says what goes first? Exponents. Your exponent. So until you know what that exponent is, you cannot multiply by 25. Okay, so our recursive rule, guys, stop talking, listen. Our recursive rule, we need the first term, which is, so f of 1 equals 25. So every term after that, f of n, is the previous term. How do I write that? Very good, Connie. F of n minus 1. And what am I doing to every term after? I'm not adding, I'm multiplying by 3. Okay, so we have now written both rules. Okay, one more together. The bungee jumper.
Oh my god, that's an example?
Okay, our bungee jumper jumps from a bridge. The table shows the bungee jumper's height above the ground at the top of each bounce. The heights form a geometric sequence. What is the bungee jumper's height at the top of the 5th bounce? Now, I'm well aware that I could just continue my table and I would get my answer. But let's use these formulas that we just spent time writing. So we're going to use, if you want to just plug in any number you want, which one's more efficient for us to use, explicit or recursive? Explicit. So our explicit rule requires us to have the first term. Do we have it?
Yeah.
Okay. So what's my first term? 200. It also requires us to have the common ratio. I don't have that yet.
There you go.
How do I find the common ratio?
200 divided by 80.
No.
Okay.
You're close.
Like
Minus 80 times
divided by, wait,
30.
You have to divide.
80 divided by 200.
Okay, good. Because it's decreasing, right? If you divided 200 by 80, it would get a number larger than 1, which would not decrease my numbers, it would increase it. So I need the second term over the first term. You have to go backwards, right? If you had 3, and then you had 9, and you had 27, how do you, I know that you guys can look at that and tell me that the ratio is 3, but how do you get 3 from that?
I do 9
divided by 3, right? So the second divided by the first, we're doing the same thing.
2 over 5.
2 over 5. Good. So now, my formula, my explicit rule, f of n equals, help me fill that out,
F of n equals
200 times
times
2 over 5.
2 over 5 to the power of n minus 1.
I have to say it like the power.
Okay,
Yeah, kind of.
so now, if I'm trying to find the height after the 5th bounce, what do I know about what I need to plug in?
You plug it into n.
What is n then?
N is an exponent.
N equals,
200.
no, n. What am I plugging in for n?
5.
5 for the 5th bounce. So I've got 200 times 2/5, 5 minus 1. What's 5 minus 1?
4.
4. So now, the beauty of this is you can plug it into your calculator all at the same time, but you need to be really careful, okay? So, 200, open parentheses,
See?
2/5, close parentheses, and then the button that you use for an exponent that's not just a square,
It's a carrot.
it's a caret, looks like this, it's right next to the squared button,
Oh, then you put 4.
and then you put 4 and push enter.
That's a big fraction.
Okay,
It's like 1.
now turn it into a decimal.
I got you.
That's a decimal.
Small decimal.
That's 5.12.
Good job, Arnold.
What is it?
5.12. Quick.
5.12. Okay, and for us, it's the height, so 5.12 feet.
Wow, we're actually so smart.
Okay. How do y'all feel about that?
I actually thought that.
It's not bad. It's not bad. It's not as bad as when we did arithmetic sequences because there's not as many different routes. It's kind of
Arithmetic sequence.
there.
You're on 94.
Okay.